Okay, so today we're going to be talking about that's one thing. So I want you guys to kind of be familiar with this. I'm going to give you some practice problems for this as well, and a couple of practice problems to kind of get you just familiar with using multiple sources of energy and how to kind of pull it together. So you may want to look over this as well. Make sure you have a clear understanding of it. And how many of you guys have done the lab, the spectroscopy lab, and turned it in and got my comments?
Yes.
I did.
Yeah. Okay. So take a look at the comments. I'm giving you guys a little extra time to sit there and turn it in. One of the problems on the exam will be exactly like what I'm asking you for, right? So calculating the number of moles of photons, based upon a certain amount of energy that's being generated. Now you have to remember that the energy is going to be an additive type of energy. Okay.
Dr. Henry, I have a question. What lab do you said? The one that we used the how do you say it? The light thingy? How do you say this thing?
Spectrometer?
Yes.
Yep.
Yes, that one. Yes, that one.
Yeah, that's the lab, the modified spectroscopy lab. Yep.
Okay, so you mean that we have a little bit more time because I did it wrong, that's why. So I have to fix it.
Yep. Yeah. You guys have a little bit more time. And I'll give you a hint. There's only been one person who did everything and almost did everything right. The only thing that she messed up on was unit. That was Selena. So if you're having questions, you may want to hit either Jessica up, because I'm sure that Jessica kind of gave Selena a little bit of guidance. Is that right, Jessica?
Yes, we worked it out together.
Good.
Yeah.
Me too. I'm gonna be going to Jessica soon.
Okay, sometimes I'm just there, hanging out with Cassie. Cassie's like my buddy.
So yeah, hit up the tutors, and you guys also know that there's Cameron as well. So Jessica, you may want to give Cameron a heads up that she may get a little couple of visits. So.
I will.
Let's see. So today we're going to be talking about molecular structure and polarity. So a lot of what we're going to be talking about is called the valence shell electron pair repulsion theory, or VESPA theory. Okay. So, and all it is basically now we're going to be taking into account lone pairs and how lone pairs kind of affects our structure, in addition to how many different atoms are attached to that center atom. And so you guys are all familiar with using Lewis dot structure and all that stuff. So it should be like a piece of cake for you, right? Yes, no, maybe?
Yeah.
So we're also going to be talking about polarity and bond polarity, and then also molecular polarity and the distinction between the two. Okay, so let's go. Okay, so we kind of touched on this the last time. I know it was the last part of the lecture, but if we take a look at this guy, we have a carbon atom here. We have a hydrogen, and an oxygen. Now this oxygen is kind of unique because we know that it has lone pairs sitting on it, right? Based upon the octet rule. So because these guys have lone pairs sitting on them, it's actually going to affect the shape of the molecule itself, right? So you guys remember geometry? Anybody? So what is the angle of a circle?
360.
Okay. So a circle is, if we go from 0 all the way back around, it's 360 degrees. Okay. So if we break up a circle in a third, what would be the angle of each of the pie slices?
120.
Okay, if we break up the angle into a fourth, then what's the angle of each of those pie slices?
90.
90 degrees.
And then if we break a circle up into a half, what is the angle of that one?
180.
Okay. Okay, good. Okay, so in the case of this, we have 3 attachments. So basically, in theory, this guy should be a 120, a 120, and a 120. However, we actually have 121, 121, and 118. So the reason why we have 121, 121, and 118 is because we have these lone pairs. I wish Abby was here. Abby made a beautiful analogy this morning. He says, so the lone pairs are kind of like hands that are pushing the other sides down, right? So that's essentially what it's like. So these lone pairs are pushing both of those other attachments down a little bit. So changing its angle, its bond angle to 118. You guys get that?
Yes.
The amount of lone pairs matter depending on what degree you're going to get.
Yes, the number of lone pairs are going to also affect the degree. So the less lone pairs, the less push it's going to have. The more lone pairs, the more push it's going to have. Yeah, but that's a very valid point. Okay. Okay, so here we have an example of a molecule that is linear. So when it's, let me go back ahead of myself. So this guy here is called the angle that we have. Since you have 3 attachments, they're all going to be in the exact same plane. Have you ever played with a widget spinner?
Yes.
With 3
Yes.
prongs associated with it. So if you look at it, right, that widget spinner is basically planar, meaning it's kind of flat, right? There's no 3-dimensional structure to it. You just kind of stick it on your finger and then you twirl it, right? It's all kind of flat in one plane, essentially, an XY plane. Okay, so this guy is going to be called Trigonal Planar. So when we talk about electron pair, geometry, and for kicks and giggles, we're just going to call it EPG. EPG is counting all the number of attachments, including what we have for our lone pair on that center atom. Okay, so this center atom has 3 attachments. So its electron pair geometry is going to be trigonal planar. Tri meaning 3, planar meaning in the same plane. Its molecular geometry is also going to be trigonal planar. Because it has 3 things attached to it and you don't have any lone pair electrons that are shifting the structure. Okay, so this guy, we have our center atom is beryllium. We have fluorine on both sides. Now the fluorines have the same number of electron pairs, so they're not going to affect the other one as much because it's going to have the same effect on both parts, so it's going to kind of keep it that linear structure. So you're not going to have a bent or anything like that as a result, okay? Because they're going to have that same effect because there's the same atom on both sides. So in this case, this guy is its electron pair. We take a look at it. There's no electron pairs on it, but there's two attachments. So this guy is only going to be linear. And then in the case of the molecular geometry, linear. Okay, good so far?
So you're saying the electron pair geometry has to do with the electrons, right? And the molecular geometry is like how the structure would like physically look, right?
Yes. So, and
In a sense.
In a sense. So what we're saying in terms of the electron pair geometry deals with both the electron lone pairs of electrons as well as the attachments, okay? And the molecular geometry really deals with the attachments, but can be modified by the number of electrons.
Okay.
Okay. So I'll give you guys an example. You'll start seeing what I mean by that and that little slight semantics to it here in a second. Okay, so here we've talked about the linear case where we have that center atom and we have two things that are attached to both sides that are going to be equal. Example, beryllium dihydride. And so in this case, it forms a linear structure. The angle is 180, right? So here's the example of trigonal planar. I'm actually going to type it out because I know that it's really hard to see on the slides. So can you guys see that, or is that too small? Better?
Yeah, I think that's good.
Okay. So as I said, this guy, because we have three attachments, this guy, or in the case of boron trihydride, this guy would also be trigonal planar. Okay. Now, if there were electrons here, right, the electron pair geometry would also still be the same because the electron pairs are going to count as an attachment for the electron pair geometry. The shape, the molecular geometry will be different. Okay. So here we have four attachments, or four things attached to that center atom. In this case, this guy is going to be tetrahedral. In this case, we have five things attached. So we're going to have one at the top, one at the bottom, and then we're going to have like a trigonal planar in the middle. So the angle between here and here, that's going to be 120. And the angle between here and here, that's going to be 90. So, and this guy is going to be called Trigonal Bipyramidal. And then in the last case, we're going to have like a square in the middle. So we're going to have 90, 90, 90, 90, and then 90 here and 90 there. So all the angles are going to be 90. That is going to be octahedral. Okay. Are you with me?
Yes, that looks familiar. What's in the other lab? The one that it's due tomorrow.
Yeah. Yeah. Which is going to get extended a little bit. Okay. So this guy has 4 attachments. So its electron pair geometry is going to be what? It's EPG. Can you guys give me 1 second? Sorry. Okay. So what is the electron pair geometry?
Tetrahedral.
Tetrahedral. What about the molecular geometry?
The same.
It is going to be exactly the same. Because there's no lone pairs to modify it, it's going to be exactly the same as the electron pair geometry. So the angles in this case are all going to be 109.5. So that's going to be 109. That's going to be 109. These are going to be 109. These are going to be 109. Okay. Pretty good so far? Not too hard?
No, it's pretty simple.
Okay. Okay, so here we're going to be looking at ammonia. So if we draw the chemical, well, this is basically showing you the shape of ammonia, but we know that the Lewis dot structure for ammonia is okay. So because we have these lone pairs, right? These lone pairs are going to affect the shape, the molecular shape of the compound, but it's not going to affect the electron pair geometry. Electron pair geometry is going to be as if it has 4 attachments. The lone pair is going to count as an attachment. So what would be the electron pair geometry?
Trigonal planar.
Not trigonal planar. Now remember, if this acts as if it has 4 attachments, so how does it act? I mean, what was the shape if you had 4 attachments before?
Tetrahedral.
Tetrahedral. So it's going to have the same number of attachments. The lone pair is going to count as an attachment for the electron pair geometry. So it's going to be tetrahedral. Now the molecular geometry, now that's going to be altered because the lone pairs, they affect the geometry, but we don't see those electrons there. So it's no longer going to be tetrahedral. In this case, it's going to be trigonal pyramidal. Because the electron pairs are going to kind of act like hands and kind of push it down a little bit further. So if it was fully tetrahedral, each of these angles would be 109 degrees, 109.5 degrees, sorry. Instead, the angles that we have now are going to be 106. They're being altered. So these guys are now going to be 106 from each other. And this guy is going to have a larger angle because it's going to be pushing things down. Okay. So in that case, we're not seeing these lone pairs because the lone pairs are invisible to us in terms of the molecular geometry, in terms of what we were able to see structurally. But it pushes these guys down a little bit more, right? And so it forms what we call a pyramid. Does that make sense?
Yeah.
Was that yes or was that a he?
Oh, yeah.
Okay. Okay, so then that brings us to our nice little table here to kind of help us understand the molecular geometry versus the electron pair geometry. Okay, so if we have 2 things that are attached and there are no lone pairs, it's going to be linear, right? So 2 things attached to our center atom, it's always going to be linear, okay? If we have 3 attachments and no lone pair, it's going to be trigonal planar. If we have 3 things are attached, but one of them happens to be a lone pair, like in this case right here, then our structure becomes bent or angular. Okay, and in this case, the angles between the 2 atoms or 2 atoms that are attached, that's going to be less than 120, where before it was everything was 120. If we have 4 things attached, our angle is going to be 109.5, and it's going to be tetrahedral. If we have 4 things attached, one of them just happened to be a lone pair, then that's going to be trigonal pyramidal. And then if we have 4 things attached, 2 of them happen to be 2 lone pairs. This guy is going to be bent or angular. Okay, and then the angle between here is going to be, it's going to be less than, much less than 109, where this one is going to be just a little bit less than 109. Okay, and so when Matt was sitting there saying, well, the more electrons that we have, the more bending you're going to have, right? So does that make sense?
Like the electrons for like the lone pairs?
Yes.
Oh, okay.
Yeah, I should say the more lone pair electrons you have, the more bending you're going to have, right? So here we only have those 2. It's going to give you a little bit of bending. This 1 lone pair, and then here you have 2 lone pairs, so it's going to give you more bending. So then as a result of that, you're going to have a smaller angle between the 2 attached atoms.
Oh, okay.
Okay. So here we have 5 attachments. What is the structure? With no lone pairs.
Trigonal Bipyramidal.
That's right. So that's going to be trigonal bipyramidal. So in other words, a pyramid on top and on bottom, a 3-sided pyramid on top and bottom. Okay. So in the case of 1 lone pair, then that's going to change it to seesaw or sawhorse. I didn't know what a sawhorse was, so I had to look it up. And then I felt silly because then I'm like, oh, I guess I do know what a sawhorse is. So you guys have seen a seesaw. You guys may not, because I don't know if you guys play outside or played outside as kids.
I mean, I know what a seesaw is, but I don't think I've ever heard of a sawhorse. No idea what that is.
It's just the thing that they used to use to saw pieces of wood. And so you hold the piece of wood between it and you just kind of let it, yeah. Okay. And then if we have 2 lone pair electrons, then we're going to get a little T shape, but that T shape is going to be a little shifted a little bit. And then if we have 3 lone pairs, then it's just going to end up being linear, because all the 3 lone pairs are going to be in the same plane together, and then the 2 attached atoms are going to be as far away as they can possibly be from it. Okay, and then in the case of 6 attachments with no lone pairs, octahedral. If we have 6 attachments and one of them happen to be a lone pair, so then that guy is going to be square pyramidal. So that lone pair is going to be at the bottom. It's going to be kind of pushing the 2 up, and so it's going to form like a little pyramid at the top. In this case, where you have the 5 attached items. So, and then so you'll have a 4-sided pyramid forming. And then in the case of 2 lone pairs, well, the lone pairs are going to alter themselves as far away from each other in this case. And then the attached atoms are all going to be in the same plane. So it's just going to form a perfect square. And next, if we have, again, 6 attachments with 3 of them being lone pairs, and then the other 3 being attached atoms, in this case, we're going to form a T shape. And again, it's going to be altered a bit because the lone pairs are going to be pushing it down. So you're going to have an altered T. And then lastly, we're going to have, in the case where we have 6 attachments, 4 of them being lone pairs, the atoms are going to be as far away from each other as they can be. So they're going to form a linear structure. Okay. Questions? Concerns? Cash? Okay. So here we have CFL3. Okay. So what does the Lewis dot structure look like for this? Who's going to be in the center?
Chlorine.
Okay. So we're going to have fluorine attached here.
Around is gonna be F. Chlorine.
Okay. So its electron pair geometry is going to be what?
The Trigonal Bipyramidal.
Okay. So it has 5 attachments. So it's going to be trigonal bipyramidal. Its molecular geometry is going to be so it has how many lone pairs now?
Two.
It has 2 lone pairs. And we have 3 atoms attached. Let's go back to our little table. Oops. Oops. Away. Okay. So we're down here, 5 attachments total, 2 lone pairs. So that's 2 lone pairs. What shape is that going to be?
The T shape.
Okay.
Dr.
So
Henry, are we allowed to use this chart during the test?
that's a good question. I'm debating. I've let people use it in the past. Okay. So in this case, you can kind of see that T-shaped form, right? Okay. Do you guys get it? Makes sense?
Yeah.
Me this chart on figure 719. Is there a way we have access to maybe print this out a little bit larger?
I believe it's in your.
Is it?
Yes.
Although I don't know if I have this particular chart. I think I limited. Yeah. I'll give
Yeah,
you guys.
there's one that's kind of like this one.
Yeah, but it's not quite. It doesn't give you all of them. So yeah, you should have access to the slides. Oh, I have to put them up. I'll put the slides up so you guys will have access to the slides. So you should be able to just to print out a base of that. So
Thank you.
okay, so it's also in the book. So you could probably get even a better image from the book. So, and you guys have, there's a copy of the book on the Canvas shell. Oops. Crap. Okay, so now I'm going to have you guys determine the Lewis dot structure for carbon dioxide, BCl3, and ammonium. And then, so we're going to do the Lewis dot structure. Then I'm going to show you how to draw the wedge dash. And then we will predict the electron geometry and the molecular geometry. Okay, so what would be the Lewis dot structure for carbon dioxide?
With carbon in the middle.
Okay.
So would we also have to take into consideration a formal charge?
Okay.
Was that a yes?
Yes.
Okay.
So if we did that,
So for the lab, that's like I don't remember what the number is. It's about this. Did you want us to prioritize the formal charge or the octet rule?
for the lab, that is a good question, because there's some of them. So let's formalize the formal charge.
Okay.
That'll kind of keep you honest. So that, okay, so let's see, formal charges of the oxygens. What do I use to calculate it? What is the first thing I use for calculating the formal charge?
The number of valence electrons.
Number of valence electrons. How many valence electrons does oxygen have?
6. Then the number of lone pairs, or minus the number of lone pairs.
Okay, so 4. And then how many bonds?
2.
Okay. And then what about carbon? Number of lone pair?
There's no lone pairs for carbon.
Okay. So 0 lone pair. How many valence electrons?
4.
And then we subtract the number of bonds. How many bonds?
4.
Okay, so perfect, right? So this is a good, valid chemical structure. What about for BCl? Who's going to be center?
Boron.
Okay, so we have boron in the center. It has 3 valence electrons. What are we going to do next?
Wouldn't be Cl on the sides?
Okay. Okay, so if we go at formal charges, okay, boron has how many valence electrons?
3.
And then how many lone pairs?
None.
And how many bonds?
3.
3. 3.
Okay, Cl,
7 valence.
number of lone pair. Lone pair electrons,
6.
number of bonds,
1.
okay, so then that equals 0. Okay, and in the last case, who's going to be in the middle?
Nitrogen.
Okay. So okay, so formal charges are already calculated. Everything looks good. Okay, so when we talk about the wedge dash diagram, that's mainly when we're trying to show things that are three-dimensional. So the wedge represents what's coming out towards you. So in the case of the nitrogen, of the ammonium, we'd have a hydrogen that would be coming out this way. And then we'd have one that's going to be going towards the back. We'd have one that's coming up. And that's one that's going to be in the same plane. Okay. You guys see that? So this represents the wedge, and that represents the dash. So if you're trying to show something that isn't planar, that actually has a three-dimensional type structure to it, tetrahedral, when you could do trigonal pyramidal, octahedral. So those guys, you're going to have a wedge dash type of structure. Things that are linear or that are planar, you don't need to do that. Okay. So here's your structure here. And in this case, our wedge dash doesn't include the electrons. So it's just you'll see just the Cl, or it doesn't include the lone pair electrons. So you'll just see the Cls following it. And then in the case of the carbon dioxide, same thing. Okay. Questions, concerns, dash. Okay, so what will be the EPG for the carbon and carbon dioxide?
Linear.
What about boron tetrachloride?
Trigonal planar or pyramidal, whatever it is.
Pyramidal? Do you have electron pairs that are going to be pushing it down?
Oh, so it's trigonal planar.
That is correct. Okay, and then what about for the ammonium?
Tetrahedral.
That's right. Okay. What about MPG? Or MG, not MPG. The molecular geometry. For carbon dioxide.
Wouldn't it be the same? Linear?
Right. Okay. What about for boron tetrachloride?
Same.
Okay. And for the ammonium.
The same.
The same, that is correct. Okay, piece of cake? Yes, no, maybe?
Yeah.
Okay, clear. Okay, so what about the Lewis dot structures for sulfur tetrafluoride and xenon tetrafluoride and water? Almost forgot about water.
Sulfur is in the middle.
Okay, sulfur would be in the middle. Okay, so I'd have is there going to be a lone pair somewhere? Any lone pairs?
There'd be electrons around the S.
Okay, so we have lone pairs around the S. Okay, so if we did our formal charges, our S is going to have 6 valence electrons. We have 2 lone pairs, and we have 4 bonds. And then our fluorine, 7 minus 6 minus 1. So it works out perfectly. Okay, so that's a good structure. Okay, so what is the the wedge dash diagram going to look like?
Tetrahedral? Oh, no.
So how would I draw my wedge dash?
Would it be trigonal pyramid?
Trigonal pyramid? So let's start with our EPG. So how many attachments do we have?
4.
We have 4?
5.
5. So we have 5 attachments. Okay, so what would be a 5 attachment?
The octahedral.
Are you sure? For 5?
Or the trigonal bipyramidal.
Okay, so it's going to be trigonal bipyramidal. Okay, so trigonal bipyramidal. Oh, so that basically means that we'll have 3 in a plane, 1 on top, 1 on bottom. Okay, so, and our MG,
Seesaw?
right, seesaw. Okay, so if we drew this guy, it'll look something like, okay, so these guys are gonna act like your seesaw, and then that guy is gonna be acting in the same direction. So it'll be like this with the 2 things on the bottom. Okay, so what about water? Who's gonna be in the middle?
H, hydrogen.
Hydrogen's gonna be in the middle?
Oh no. Oh, I mean oxygen.
Okay. So we have hydrogen here, and do we have any valence electrons?
Yeah, you have 2 lone pairs for oxygen.
Okay, 2 lone pairs. So our EPG is gonna be
A tetrahedral.
okay. Our MP, or MG, sorry, MG.
Bent.
Okay, and so it's gonna look like. Okay, what about xenon tetrafluoride?
Xenon in the middle.
Okay. We know that it has 8 valence electrons. So, sorry. Okay. So the EPG,
The octahedral.
Hydro.
okay. And then the MG,
A T-shape.
so we have 2 lone pairs and
Oh.
4 attachments.
The square planar.
There you go, square planar. Questions, concerns, Cash? No questions? Okay. So is it pretty simple?
Yeah.
Good. Okay. Okay, so sometimes we're going to have to do this with molecules, bigger molecules than just, 4 attachments attached to it. So in this case, we have this nice amino acid chain here. So in this situation, what we'll do is, I kind of got carried away, I showed too much too soon. So the way that we write this out, the way it's written out kind of helps us establish the structure. So we know that we have an N, and there's 2 hydrogens that are going to be attached to that N. And that N is going to be attached to either this carbon or that carbon. Well, it's not going to be attached to this carbon because it will make it a terminal carbon. It'll be because carbon can only have 4 attachments at most. It can't have 5 attachments. So more than likely, it's going to be attached to this one. So we'll have that C, we'll have that H, and then this carbon here is going to be attached to this carbon. And then this carbon is going to have 5 hydrogens around it. Or not 5, I'm sorry, 3 hydrogens around it. So it'll have 4 attachments because then we'll have it attached to that carbon. And anytime that you see OOH or COOH, you always have a carbon that's double bonded to an oxygen. It has 2 lone pairs. And then you have an alcohol group, an OH. Okay? You guys see that? Okay. So in this case, what would be the electron pair geometry for this part here, this center atom? It's a nitrogen.
Tetrahedral.
Okay. What about the molecular geometry?
Trigonal pyramidal.
Okay. What about this carbon?
Would be a tetrahedral for both.
Okay. So the EPG would be tetrahedral and the MG. This carbon?
Wouldn't it be the same tetrahedral?
Okay.
For both.
Okay. this carbon.
Trigonal planar, right?
Okay. And that's for the EPG.
Yeah.
Okay. And what about the MG?
It would be the same since there's no lone pairs.
That's right. Okay. The oxygen here.
The EPG would be linear.
Okay. Are you sure?
Tetrahedral.
Okay, so we have linear and tetrahedral. How many say linear? Raise your hand. Put your thumbs up for your reaction. Okay. How many say tetrahedral? Okay. So the correct answer is tetrahedral. Okay. What about the MG?
That one would be linear, or would it be like bent depending on the bond polarity?
Technically we have lone pairs. So those lone pairs are going to be pushing them down, so it'll be bent.
Oh.
Yeah.
Oh, so it's always bent when it has lone pairs.
That's right.
Mm.
When you have two lone pairs. So okay. Questions, concerns, Cash?
Does it matter if the lone pair are both on top or if one's on top and one's on bottom?
So in theory, they're always going to be both on top. So they're both going to be kind of pushing down on the other bond. Because they're going to orient themselves to kind of both be up here. I just drew it like this. So in reality, it'll look like this. See it down here? With both of the lone pairs on top. And so it's bending, making these guys be bent in structure.
Dang.
Okay. Good question, though. Okay. How are you guys doing so far? Good. Silence means that I keep going forward. Okay, so now we're going to talk about bond polarity. Okay, so bond polarity, we've already kind of talked about it with electronegativity. So the one that's more electronegative is typically going to be pulling the electron towards it, right? And the one that's less electronegative is going to be, giving up that electron a little bit. Okay, so but that's going to be a partial type of structure. So here, the electronegativity between hydrogen and carbon is going to be very, very little, right? So the difference between them is going to be very small. So there's going to be a little slight bond polarity, but in reality, it's going to be so little that it's not going to be noticeable, okay? So when we talk about bond polarity, we're talking about just the polarity between two atoms, these two atoms, okay? So in the case of here with boron and fluoride or fluorine, then in this case, whose electronegativity is more, boron or fluorine?
Fluorine.
Okay, fluorine is going to be much larger compared to boron. So it's going to have a stronger pull towards that electron. So the pull is going to be, or the dipole moment is going to be pushing towards the fluoride or fluorine ion. I mean the fluorine, not ion. Okay, questions? Okay. So the dipole moment is going to be going towards the fluorine in that case. Okay. So when we talk about molecular polarity, you have to take into consider, oops, got carried away. you have to take in consideration both the bond polarity and the molecule as a whole, okay? So in the case of carbon dioxide, the bond polarity, oxygen is more electronegative than carbon. So the electron is going to be moving towards the oxygen, all right? So we're going to have a dipole moment towards the oxygen, okay? But we have an oxygen going on both sides. So basically you're going to be pulling evenly on both sides, right? So if I'm like sitting in a chair and then I had twins that are on both sides of me that were the same strength, so is either of them going to pull me more than the other? Or am I just going to sit here in the middle between the two?
Stay in the middle.
I'd stay in the middle. So in that case, there'll be no overall dipole moment. So in this case, this has no polarity associated with it. So it's considered to be non-polar. Okay, so in the case of oxygen and in water, so the dipole moment is going towards the oxygen, from the hydrogen to the oxygen, from the hydrogen to the oxygen, because oxygen has a stronger electronegativity. So in this case, the overall dipole moment, since both electrons are going in that direction, it's going to be like an additive effect. This one is going to be kind of like an opposite, so a subtractive effect. Okay, so in this case, your dipole moment is going to be moving towards the oxygen. Okay, and so this guy is going to be a polar molecule. Where this guy is going to be a non-polar molecule. Does that make sense? So in this situation, these guys are canceling each other out since they're going opposite directions. Since these guys are going both the same directions, they're going to be adding towards each other. Are you with me? Alberto, are you with me?
Yes.
Good. Okay, so we'll see. There's 11 of you guys. Oops, got carried away again. Okay, so I have two molecules. I'm going to split you guys up into two groups. And what I want you guys to do is draw the Lewis dot structure. I want you to tell me the bond polarity, and then I want you to tell me the molecular polarity of the two molecules. Okay? You guys got what I'm asking for?
You want the Lewis dot structure, and then you want to know the polarity.
Yep, bond polarity and molecular polarity.
Okay.
Okay, so I'm going to put you guys in groups. Okay, let's do this. Give you guys 8 minutes. And then I'll see you back here. Rooms are open. Okay, you guys are back. Okay, group one, that would be Alexandria and Angelina's group. Can you guys do the CSO? And then group two, that's going to be Alberto and Matt's group. You guys, can you guys do the what is it? Carbon, tetra, hydrogen, chloride. I'll clear off my screen.
You just want the bond polarity and the molecular polarity, right?
That's right. The Lewis dot structure.
Oh, and the Lewis dot structure?
Yep.
wait. Oopsie.
Did I erase your markings there? Put that back. So what will be the bond polarity for group 2? I saw Taylor do this. What about over here?
The hydrogens point towards the chlorine.
You mean the carbon's going to point towards fluorine?
Yes.
Okay. So overall, you're right. It's a polar molecule, and it's all facing towards the chlorine for the second one. Okay, what about with the bond polarity? Who's going to be favored under each circumstance? Which way is it going to be pointing? Is it going to be pointing towards the carbon in the case of the sulfur and the carbon, or is it going to be pointing towards the sulfur?
Like, what do you mean?
The bond polarity, the bond between carbon and the sulfur. Who's more electronegative?
Carbon or sulfur?
Sulfur. So it's going to be pointing in this direction, right? For the individual bond. Okay. So, and what about in the case of the carbon and the oxygen?
It's going to be pointing towards the oxygen.
Okay. So overall, if we add these two together, it's going to be pointing towards whom?
Towards the oxygen.
Towards the oxygen? Okay.
Yeah, because it's
So-
more electronegative than sulfur.
That is correct. So yes, because the oxygen is more electronegative than the sulfur, it's going to have more pull overall. And so the overall molecule is going to be a polar molecule pointing more towards the oxygen. Even though they're going to kind of cancel each other out a little bit, you're still going to have some that is going to be going towards the oxygen. Does that make sense? So it's being kind of a little more numerically active, correct? Is that, so if you have the oxygen here and the sulfur there, these guys are going to cancel each other out a little bit, but the overall polarity is going to be going towards the oxygen, right? Not as strong as it would be since they're going in opposite directions. Does that make sense?
Yeah.
Okay.
Yes.
I have a question.
Yep. Oops.
Is there a way to use the polling table to get a little bit more accurate on which element is like, so how like they both cancel out, but it goes more towards the oxygen?
Yeah. Yeah. What you would use is the electron negativity difference, right? So do you remember that table in chapter 6, I believe it was, with the electronegativity, where electronegativity goes from 0 to 4, and fluorine is the most electronegative, and then oxygen is the second most electronegative. And you remember that? Let me see if I can find it for you. It's the easiest way of doing it. Give me 1 second. see. So here are basically electronegative values, although it's flipped. Let me see. Let me go to P table. Hold on. That's where I got it from in the first place. Okay. Can you guys see the electronegativity table? So this basically is just showing us all the electronegativity. We'll make it red. Okay, so from yellow to red, the ones that are more electronegative are showing up here. So you guys can get an idea of what the electronegativity is relative to the other. So in the case of oxygen compared to sulfur, so oxygen is 3.44, and then sulfur is 2.58, right? So oxygen is clearly much more electronegative than sulfur. It's almost a full point more electronegative. So sulfur is just a little bit more electronegative than carbon. You guys see that?
Yeah.
So we're looking at that value down here, right? So yeah, it's favoring sulfur, but they're almost equal. So they could almost be neglected, but the oxygen accounts for the most of it. So that part is just going to be pushing it, driving it to the other direction completely. Okay, does that make sense?
Yes.
Yeah. So does that help out, Taylor?
Yes.
Okay. Okay, hold on. Okay, so we're going to stop here. And on Wednesday, we'll finish up these last questions. So kind of be prepared for them.
Did you post the test?
The test is actually going to be posted tomorrow morning. So it's
Until
going to
when?
open, and you guys have until next Monday.
Oh, okay.
Okay. Yeah, since I posted the practice test a little late, and then there's one of the problems that it's not showing all of the answers, so it needs to be fixed. It actually isn't showing the question correctly either, but it needs to be fixed. So so you may see a change in that as well too for the practice. Okay. Any questions?
Will we have a lab on Wednesday?
There will be a lab on Wednesday. The lab on Wednesday is going to be observations of intermolecular forces. In other words, you're going to be making slime.
Oh.
Okay. Let's see. There was also one other thing that I wanted to talk about real quick before I forget. Then I'll let you go. Okay, so I wanted to mention let's say both of these are 3p. They're just two different molecules in a 3p. So in one are atoms. So in one case, let's say we have this guy. And in the other case, we have so this guy would be an example of paramagnetic. This guy would be an example of magnetic. Okay, so paramagnetic basically means that you have unpaired electrons. Because you have unpaired electrons, what's going to happen? It's going to want to attract to a magnet. So in the case, those elements are going to be more attractive towards a magnet, and so they're going to, or can be adjusted by a magnet. So they'll come up like in suspension if you put a magnet around the solutions that they're in. Those guys will kind of be stuck there, okay, because they have unpaired electrons that are going to be kind of attracted towards a magnet, okay? Where a diamagnetic molecule is going to be not attracted towards a magnet. And so as a result of that, they're all matched up. So these guys are going to kind of cancel each other's spin off of each other. So if they have a pair, they're all paired up, they're not going to have a spin. So they're not going to have no type of magnetic attraction. Does that make sense?
Yeah.
Okay.
So is that top one related to like ferrofluids?
Yes, it can be related to ferrofluids. It can also be related to when you're bringing a, let's say, for instance, liquid oxygen versus liquid nitrogen. So in one case, one is paramagnetic, and in one case, one is diamagnetic. Well, the one that's diamagnetic will flow through a magnet, but if you put a magnetic field around it, the other one will stay suspended between the magnetic field. Does that make sense? So it'll look like it's floating. The liquid is floating.
Mm-hmm.
And it's funny because they actually use that for the, what is it? The bullet train in Japan. They use that technology, paramagnetic technology, to kind of help the floating of the train itself. Okay. Any questions? Concerns? Okay. Well, the real exam will be posted tomorrow morning. Of course, it's going to be worth 100 points. There's going to be probably about 30 questions. Most multiple guess. And
Well,
then
some of the questions we have to take a picture and upload it.
Yep. Yeah, you guys know the drill, right? So it's going to be proctorial, and then afterwards, at the end of it, you take a picture of your answers, and then you're going to upload those. And then when you guys take a picture, can you make sure, because I know that a lot of you guys have iPhones, make sure you take still pictures, and then you upload the still pictures, not the HEIC.
Yeah, if you have an iPhone too, they can auto scan them as PDFs.
Yes, that would be even better, because PDFs are a lot easier for me to read in Canvas. Okay.
Oh, I just want to make sure we are allowed to use P-table during the test, right?
What was that?
Are we allowed to use P-table, like ptable.com during the
Yes,
test?
I'm actually going to have that available so that you'll have, you can be able to click on it. Yes.
Okay.
Anything else? Yes, this video will. So this video will be uploaded on probably tomorrow, because it usually takes till tomorrow morning is when I'll get the proofs of it. So for the video itself. So early tomorrow morning, around 2 o'clock in the morning. I won't say it'll be uploaded then, but sometime at that point. Any other questions?
Wait, Dr. Henry, you said that tomorrow you're going to be grading the video?
No, somebody asked, when will this video be uploaded? So the video for this lecture, when will it be uploaded? It'll probably be uploaded sometime tomorrow. Because I don't get I don't get the videos until in the morning. So when I have an evening class, I don't get it till the next morning.
Okay.
Okay. But we went over pretty much the same thing in the morning class. So, and it'll probably be loaded probably tomorrow as well too. But earlier tomorrow. So, okay.
And there's no lab tonight, right? Our next lab won't be till Wednesday.
Yep, your next lab is to Wednesday. The other one is, so we kind of talked about it last week where you're cutting out the tiles and you're drawing the Lewis structures and all that stuff.
Oh yeah, I'm almost done with that one.
Yep. So that was tonight's labs. Okay. So then I'll see you guys on Wednesday then.